Alright, welcome back. Math 1910. We're going to look at Chapter 2, Section 1. We're going to look for, what is a derivative, and we're going to solve the tangent line problem. Alright, so we're going to take a look at the derivative and the tangent line problem as we work through this. So we should be able to find, after this, the slope of the tangent line to a curve at any point. We should be able to use the limit definition, alright, to find the derivative of a function. And we want to understand the difference or the relationship between differentiability and continuity as we go through this. Alright, so just a little background, right? We know that, kind of where this came from. This is how calculus kind of came about, okay? European mathematicians, and they were working on these different problems here. The tangent line problem, velocity and acceleration, minimum and maximum problem, and the area problem. And essentially, it comes down to calculus solves all of these problems. So when we do this, they all involve a limit, require a limit, and we can do this all using calculus. So what are we really talking about when we're talking about a tangent line problem? What we can do is we can use the secant line to find the tangent line. The tangent line would be, and we want to find the slope of the tangent line because we want to find the rate of change of any graph at a particular point. And we would find the slope of the tangent line because it's one point that's tangent to the graph. Now, for us to find the tangent line, we can use the secant line. The secant line is using, point slope. So we have, or we need two different points here so we can actually calculate the slope for this. All right, so notice our slope, right? Our change in x, or our delta x, is shown on the bottom. Okay, so it's c and c plus delta x, and then we have our change in y. Okay, so we're evaluating. So it's f of c plus delta x minus f of c. Okay, so that's where your delta y came from. You're used to talking about slope as change in y over change in x, or y2 minus y1 all over x2 minus x1. We are doing the same thing here. Okay, so our point of tangency tends to be c plus delta x and f of c plus delta x. Okay, so that's our new point that we're doing. So that's kind of like finding our y2 minus y1 divided by x2 minus x1. That's our slope. So we can see that in calculus that translates to f of c plus delta x minus f of c divided by c plus delta x minus c. Okay, and that simplifies down. So the slope of the secant line is known as f of c plus delta x minus f of c divided by delta x. That's literally change in y, change in x, and this is where everything was derived from that you use in your algebra classes. Okay, so that's really all we're breaking this down to: change in y, change in x, and we can get a better approximation based on what we do with changing x and y. So as you can see, the smaller increments that we change delta x, okay, we're going to get smaller increments of delta y. And as we make very small changes, we're going to get much more accurate using the secant line to approach the tangent line. So you can see each methodology here. As we make delta x go to 0, we're taking smaller and smaller chunks of x. We're going to get much more accurate with what our f of c is, so our actual slope at that point. And this is where we're going to actually start, calculating the slope of different functions. Okay, you know how to calculate the slope right now of anything that's linear, right? You use y equals mx plus b. You know that m, is change in y over change in x. We are going to apply all this now to, other functions. So I want you to write all this down. This is the definition of the tangent line, okay, and how we find the slope. Okay, so if f is defined on an open interval containing c, and the limit, okay, of delta y over delta x as delta x approaches 0 is equal to the limit of f of c plus delta x minus f of c divided by delta x as delta x approaches 0 is m, the slope. Okay, so if that exists, then the line passing through c, f of c, with a slope of m is the tangent line to the graph of f at point c, f of c. Okay, otherwise known as slope. So this is using slope, or calculating slope using the limit method. Okay, so let's do an example here. We want to find the slope of a graph f when c is 2. All right, so we can apply the definition of slope to the tangent line. So we're going to use the function here, f of x equals 2x minus 3. So we have to make sure that we're substituting everything in correctly. So c is 2, okay? So we're going to do f of 2 plus delta x minus f of 2 divided by delta x. Okay, so when we substitute that in, everywhere there's an x in the first part, we have to substitute in 2 plus delta x. Okay, and then the second part, we're going to substitute in 2 into f of x. So that gives us 2 times the quantity of 2 plus delta x minus 3 minus 2 times 2 minus 3 all over delta x. Okay, so we're just using the definition here, and we substituted in 2 plus delta x in for x, and we substituted in 2 into f of x to get the values that are in the numerator. Okay, now we got to simplify down, do our math, so we end up with 4 plus 2 delta x minus 3 minus 4 plus 3 all over delta x. So we want to be able to, combine like terms. We have a positive 4, negative 4, those cancel. We have positive 3, negative 3, those cancel. All right, so we are just left with 2 delta x over delta x, and the delta x's cancel, so our solution is 2. All right, so the limit of f of 2 plus delta x minus f of 2 all over delta x, all right, as x approaches 0 is 2. Now, notice how that equates to what you learned in algebra. Look at the equation. F of x equals 2x minus 3. M is 2, right? The slope is 2. You could do that from algebra. Notice the limit as delta of x approaches 0 is also 2. That's the slope. So that's how we use the limit method to calculate the slope. Now, it's very easy for you to do that when we have something that's linear. It gets a little bit more complicated when we get something that's nonlinear, okay? All right, but let's take a look at the graph of this real quick. All right, so this is really what's going on, right? Change in y over change in x. Change in y is 2. Change in x is 1. 2 over 1 is 2. So this is kind of how you would have done it, old school wise, when you first learned algebra. All right, now what we got to do is pay attention to the fact that the tangent line problem, okay, the limit definition, it doesn't cover the possibility that we might have a vertical tangent line. Okay, you can see right here, if we have f of c plus delta x minus f of c all over delta x, as delta x goes to 0, if that equals infinity or equals negative infinity, all right, that's giving us a vertical line at x equals c. Okay, so we got to be careful with how we do this. And here's what it might look like graphically. Okay, the tangent line might actually be a vertical line, so we just got to be careful when we do this. So when the domain of f is the closed interval a to b, you can extend the definition of the vertical tangent line to include the endpoints, okay, by considering continuity and limits from the right and from the left. All right, so that really kind of helps you out there. So what do? We're going to do the derivative of a function. All right, so we're going to use the limit to define the slope of the tangent line. Okay, we're going to call this differentiation. Differentiation, we're going to say the derivative. All right, so this is the definition of the derivative of a function here. Notice we have f apostrophe of x. We pronounce that f prime of x. Anytime we are finding the derivative, we always write f prime of x. If we are finding the second derivative, we would have f double prime of x, so we would have 2 apostrophes. Okay, so from here on out, you need to understand that when you see f prime of x, that means we're taking the derivative of that function. And remember, that's interchangeable with y. If you see y prime, that means we need to take the derivative of the function. And how do we take the derivative? We take the limit of f of x plus delta x minus f of x all over delta x as delta x approaches 0. Okay, that's provided the limit exists, and we call that the derivative. So that's how we're going to take the derivative of a function. Okay, we use the derivative to determine the instantaneous rate of change, okay, from one variable with respect to another. So when we do the actual process of finding the derivative, we call the process differentiation. Okay, a function is defined as being differentiable at x if the derivative exists and the differentiable on an open interval. Okay, so if we can take the derivative and it's differentiable on the open interval a to b, it's differentiable at every point in that interval. Okay, so the derivative helps us find the instantaneous rate of change, and the process of taking the derivative is called differentiation for us as we go through this. Okay, there are multiple ways to write this. We can write it as f prime of x, we can write it as dy dx, we can write it as y prime. We can write it as d dx of f of x, or d subscript x of y. All of these are perfectly good notations, and we're going to use probably every single one this semester as we go through it, just so that you get used to all the different nomenclature of how we write the limit. Okay, but using the derivative, sorry about that, how we write the derivative, but we're using the limit process for right now. There are going to be some other methods that we're going to learn how to take the derivative of a function that aren't as intricate as using this method. All right, so let's find the derivative of f of x equals x cubed plus 2x. Okay, and we're going to use the definition, the limit definition, okay, to do this. Notice if this was linear, it would be easier. You'd be able to look at it and recognize right away what the slope is. However, this function's a cubic. All right, so we're going to actually figure out what the slope is. So, f prime of x, the derivative, is f of x plus delta x minus f of x all over delta x as x approaches 0. So we're using the definition of the derivative here. So what we need to do is everywhere there's an x in the function, we replace that x with x plus delta x. Okay, so we can see that that ends up giving us x plus delta x quantity cubed plus 2 times x plus delta x. So we replaced every x in the function with an x plus delta x. And then it says minus f of x, so I have to go minus x cubed plus 2x, because that's what f of x is. You got to make sure that I would keep track of parentheses, because you have to make sure that you're going to distribute that negative through correctly. Okay, and then it's all divided by delta x. Okay, next step is we have to cube out x plus delta x and distribute the 2 through the x plus delta x and distribute the minus sign to x cubed plus 2x, all in the numerator. So when we do that, we end up with x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed plus 2x plus 2 delta x minus x cubed minus 2x all over delta x. From here, we have to look for things that cancel. Okay, notice that we have a positive x cubed and a negative x cubed, so those will cancel. We also have a positive 2x and a negative 2x. Those will cancel. And then we see if there's any other like terms that we can come up with. Okay, there aren't any right now. But if we look at this function, okay, can we take the limit right now with direct substitution? No, because it's as delta x goes to 0. If we substitute that in, we're at division by 0. So what we need to do is still factor out. Okay, so what's common amongst the entire numerator? You should say delta x. So factor out a delta x out of the numerator. Okay, so when we factor delta x out of the numerator, okay, we're left with 3x squared plus 3x delta x plus delta x squared plus 2. So what does that help us do? When we factor that out, we can actually cancel out the denominator now. So now if we plug in or substitute in 0 for delta x, we actually get, okay, the completed derivative. All right, so when we cancel out the denominator with the numerator there, after factoring out delta x, we have this, all right, we have 3x squared plus 3x delta x plus delta x squared plus 2. When we substitute in 0 for delta x, the 3x delta x goes away and the delta x squared goes away, right, because they become 0. So all that we are left with is 3x squared plus 2. So that is the solution. That's the definition of the derivative, okay, using the limit method of our original function, which was x cubed plus 2x. All right, let's start talking about the relationship between differentiability and continuity. Okay, so we can write this as f prime of c now. So we're just writing the same kind of thing a little differently. We're not going to use delta x with this method, but it's still an alternate form of the derivative and works the same. So we can say f prime of c, or the derivative of c, is the limit of f of x minus f of c divided by x minus c, and we always take it as x approaches c. Because if we put direct substitution in there right now, we would have, canceling out, and we would have division by 0, which would not exist, and we can't do that. So we have to make sure that we work through our functions algebraically here. Okay, so this is just simplifying it down. So we can check out continuity. We can take a limit from the left and we can take a limit from the right. So we can take the limit as x approaches c from the left, of f of x minus f of c all over x minus c, and we can take the limit of f of x minus f of c all over x minus c as x approaches c from the right. So if they are equal, okay, if they exist and they are equal, all right, these are the one-side limits. So we call them the derivatives from the left side and the derivative from the right side. And we already talked about that, when we first started talking about limits, when we had to do the table and how x approached a value from the left and how x approached a value from the right and what that value actually was. Okay? So with this, it follows that f is differentiable in the closed interval a to b, and if it's differentiable in the open interval a to b, and if the derivative from the right and the left both exist. Okay? So it's differentiable, and we're kind of defining continuity here. That's really what we're going to get into. So here's a function, right? The greatest integer function, or the step function. Okay, it's not continuous. Okay, there's a step. So we have to take a look. So for instance, right here, the greatest integer function is not continuous at 0. So that tells us it's not differentiable at x equals 0. So this is where we have to make sure when something's not continuous at a point, we cannot take the derivative at that point. So that's what we really need to understand. If it's not continuous, okay, it can't be differentiable there. So we can verify, if we actually substitute it into the algebra. We can see that the derivative from the left is not the same as the derivative from the right. So we can conclude, all right, that it is not differentiable. So here's what you really need to understand. Differentiability implies continuity. So if something is differentiable, that means it's continuous. The opposite is not so true though. So if a function, okay, is continuous, it doesn't mean that it's differentiable. So you got to make sure that you understand that. Differentiability implies continuity, but continuity does not imply differentiability. Okay, just so you understand there. So here's a great example, and a lot of people will get kind of hurt on this one. So this function, right, this is the absolute value function. So we have f of x equals the absolute value of x minus 2. It is continuous at 2, right? This function is continuous. The absolute value function is a continuous function. However, it's not differentiable at 2 because the left-hand limit and the right-hand limit do not agree with what they're going to, okay? So you got to be very careful when you solve this one. If we do one-sided limits here, as x approaches 2 from the left, okay, it tells us it's negative 1. As x approaches 2 from the right, okay, we get a value of 1. So since the left and the right are not equal, what you just need to remember, if we have a graph that has a sharp turn or a sharp point, it's not differentiable at that point. So very important for us to retain that and understand. Okay, that's one place that it's not going to be differentiable. All right, so let's talk about and let's really get into it. Okay, a function is not differentiable at a point at which its graph has a sharp turn or a vertical tangent line. So those are the 2 points. So we can automatically tell that we cannot take the derivative of a function that's producing a vertical line at that point or has a sharp point. Okay, so differentiability, this is theorem 2.1, differentiability implies continuity. So what does that mean? If f is a differentiable at x equals c, then f is continuous at x equals c. So differentiability implies continuity. If we can take the derivative at that point, it's definitely continuous at that point. So it's, pretty much that simple. If a function is differentiable at x equals c, then it's continuous at x equals c. So just remember the term differentiability implies continuity. Now, however, it's possible for the function to be continuous at x equals c and not be differentiable. So continuity does not imply differentiability. And we just saw that with the absolute value function. Okay, how that makes a big difference there. So your homework is going to consist of, being able to take the derivative of a function using the limit method. And then we're going to define, if a function is continuous or not. So remember, if we can take the derivative at that point, the function's continuous. If we can't take the derivative at that point, okay, it's not going to be continuous most likely. But remember, Differentiability implies continuity, but the vice versa does not work. Continuity does not imply differentiability. Alright guys, that's it for this lecture. If you have any questions, email me. Let me know if we need a Zoom or Teams conference call or whatnot. Else guys, I'll talk to you later. Have a great day, and I'll see most of you in class.